Have you ever, just looked up at the night sky and felt that pull, that really human thing where you start asking the huge questions?
Absolutely. Where did it all come from? Is there anything else out there? What's the point?
Exactly. It's this quest we all seem to be on, and today we're taking a really deep dive into those kinds of inquiries.
And we've got an amazing guide for this one. One of the most brilliant minds ever, really, Stephen Hawking.
That's right. We're digging into excerpts from his final book, Brief Answers to the Big Questions.
Yeah, it's fascinating because it was finished up by his colleagues and family after he passed away. So it's like a final window into his thinking.
A unique window, definitely. So our mission today, unpack his answers, look at his own journey, and try to grasp what it all means for us, for reality, for the future.
And he does it all with that famous wit, which is always a bonus.
Okay, let's start with the man himself, Stephen Hawking. There's this amazing coincidence about his birth, isn't there?
Yeah, he was born exactly 300 years after Galileo died. He loved that connection.
He kind of saw it as destiny, didn't he? Like he was meant to reshape how we see the cosmos, just like Galileo.
He definitely did. And you can see that curiosity right from the start. Growing up in London, St. Albans, apparently playing in bomb sites, taking things apart.
Huh. Though maybe not always putting them back together.
Probably not. But even as a kid, like 12 years old, his friends nicknamed him Einstein.
Wow. Even though he said he was only halfway up the class, they saw something.
They clearly did.
Yeah.
Initially, he was actually drawn to the idea of a universe that was unchanging, everlasting. Which is funny, because his own work later demolished that idea.
But his story isn't just about intellect, is it? It's also about incredible, almost unbelievable resilience.
Oh, absolutely. Getting diagnosed with ALS at just 21, being told he only had a few years left.
I can't even imagine. But somehow that changed everything for him. He said his expectations dropped to zero, so every single day after that felt like a bonus.
It's an incredible outlook. And it pushed him, to finish his PhD, to marry Jane. Her confidence in him was apparently vital.
And getting that research fellowship at Gonville and Caius College was huge, too. It let him keep working even as the illness progressed.
Right, and he passed that questioning spirit on his son Tim, asking about tiny universes. You can just picture it.
Then came another huge hurdle, losing his voice completely after the tracheostomy in '85.
Yeah, before that, only his family could really understand his speech. Must have been terrifying.
But then technology stepped in. This computer expert, Walt Waltos, sent him the Equalizer program.
Which eventually became that iconic system from Intel, the AAT, controlled by his cheek muscle. Amazing.
And he kept that synthesized voice, the American accent one. He said he identified with.
It became his voice. And that voice allowed him to share his ideas with everyone, not just academics. That's why he wrote A Brief History of Time.
Right, April Fool's Day, 1988. He wanted to explain the universe to all of us.
And he became, well, probably the most famous scientist since Einstein. Partly the disabled genius thing, maybe. But underneath it all was just this pure drive to understand how the universe works and share that excitement.
Okay, so we have the man. Let's dive into one of the biggest questions he tackled. How did the universe actually begin? His answer really shook things up.
It did. He was pretty clear. Science, he thought, just offered better and more consistent answers than religion for these big questions.
He wasn't trying to attack religion, though, was he? More like trying to build a rational picture.
Exactly. A rational framework. He saw the laws of nature as the ultimate explanation for everything. Even his own condition, not a curse. Just physics and biology doing their thing.
He liked pointing back to ancient thinkers, too, like Aristarchus figuring out the Earth orbits the sun way back in 300 BCE.
Right, seeing stars as distant suns. That scientific impulse. Hawking's view was, you could call the laws of nature God if you wanted, but that's just defining God, not proving anything.
He famously said we might know the mind of God by the century's end, meaning we'd understand those fundamental laws.
Yeah, the laws of nature themselves.
So his big idea for the beginning, the ultimate free lunch.
Yeah. The universe just spontaneously creating itself from nothing.
Sounds impossible. How did he break that down?
Well, he said you need three things: matter, energy, and space. But Einstein's EMC basically links matter and energy. So you're down to energy and space.
Okay.
And the Big Bang, that was the moment. Energy and space just sort of popped into existence. Spontaneously invented, as he put it.
But where did the energy come from? Doesn't that violate conservation of energy?
Ah, that's the clever bit. Negative energy. Think of digging a hole. You get a pile of dirt, positive energy like matter and energy, but you also get a whole negative energy.
So the universe's positive energy is balanced out.
Exactly. By the negative energy stored in space itself. The total energy can actually be zero. It all balances.
Wow.
And then add quantum mechanics. On tiny scales, particles can just appear and disappear randomly, right?
Right. Virtual particles, yeah.
So if the whole universe at the very beginning was incredibly tiny, smaller than an atom,
It could have just popped into existence, like a quantum fluctuation.
that's the idea. Popped into existence from nothing, without breaking any laws. The ultimate free lunch.
And this leads to another mind bender. Time itself started then?
Yes. No, before the Big Bang. He said asking what came before is like asking what's south of the South Pole.
There's just no such direction.
Right. So for Hawking, that removes the whole need for a cause or a creator to kick things off.
And he took that logic further, didn't he, to things like heaven or an afterlife?
He did. He saw those ideas as wishful thinking. Said they flew in the face of everything we know in science. Pretty uncompromising.
That's definitely a viewpoint that generates discussion. But scientifically, the idea of time being part of the universe, not separate, has become pretty central, has it?
Oh, absolutely. Thinkers like Aristotle imagined an eternal universe, maybe because it seemed more perfect, avoided tricky questions about creation. Kant wrestled with it too.
But Einstein really changed the game. General relativity in 1915.
Completely. Space and time aren't just a fixed backdrop anymore. They're dynamic, shaped by what's in the universe. They're defined within it.
And then the actual evidence started rolling in, like Olber's paradox. Why is the night sky dark?
If the universe was infinite and eternal, it shouldn't be. And then Hubble's work.
Seeing galaxies rushing away, the universe expanding, that killed the old static models.
Right. And the steady state theory, the idea of continuous creation that got shot down too, largely by radio astronomy work done right there in Cambridge.
Which leads us back to Hawking, his work with Roger Penrose in the 60s. The singularity theorems.
Crucial stuff. They used Einstein's own equations to show that if general relativity is right, the universe had to have started from a singularity, a point of infinite density, a beginning.
So mathematically proving a start point.
Pretty much. And then, almost concurrently, came the discovery of the cosmic microwave background in '65.
The afterglow of the Big Bang. You could see it as static on old TVs.
That faint hiss, yeah.
Mm.
Direct proof of that early, very hot and dense state. The echo.
So general relativity points to a singularity, but the theory itself kind of breaks down there, right? You need something else.
Exactly. You need quantum mechanics, the theory of the very small. Things get fuzzy at that scale. Heisenberg's uncertainty principle.
Can't know position and speed perfectly. God does play dice.
Right. It's probabilistic. And Richard Feynman's idea of multiple histories comes in.
The universe didn't just take one path, but explored all possibilities.
Each with its own probability, yeah. This led Hawking and Jim Hartle to the no-boundary proposal.
Using imaginary time. Sounds complicated.
Mathematically, it treats time like another space dimension near the beginning. The upshot is the universe could start smoothly, with no edge or singularity, like the surface of the Earth has no starting point, no need for special initial conditions.
That's elegant. And what about the anthropic principle?
The weak version, basically.
Yeah.
The fact that we are here to observe the universe tells us something about its properties, like why 3 dimensions of space?
Because life, or even stable atoms, wouldn't work in 2 or 4.
Exactly. Stable orbits need 3 dimensions. And then there's inflation theory.
That burst of super rapid expansion right at the start.
It explains why the universe is so incredibly smooth on large scales, why the microwave background looks so uniform. Those tiny quantum jitters, the fluctuations during inflation.
They got stretched out.
Massively, and became the seeds for all the galaxies and stars. So in a way, God really does play dice with the cosmos. Those random quantum fluctuations determined everything.
Okay, from the birth of everything to, well, some of the weirdest objects in it. Black holes, another Hawking specialty.
Oh yeah, though the basic idea goes way back. John Michell in 1783 talking about dark stars.
Stars so dense light couldn't escape, but the term black hole came much later.
John Wheeler, 1967. He saw they were fascinating in their own right.
And the physics is just wild. Gravity crushing matter down to a singularity, a point where space and time end.
Effectively, yeah, infinite density. And Wheeler suggested these are always hidden by an event horizon, the point of no return.
The cosmic censorship conjecture. Keep the weirdness contained.
Sort of. And the no-hair theorem says from the outside they're incredibly simple, just mass, charge, spin, nothing else.
So what's it like, hypothetically, falling into one?
Depends on the size. So small, scalar mass one. Spaghettification. Gravity difference between your head and feet tears you apart.
Doesn't.
Not so much. But a supermassive one, like in our galaxy center, millions of times the sun's mass, you actually drift across the event horizon quite smoothly. The stretching only gets bad much later, closer to the singularity.
Still not a great destination. Now, Hawking really turned things upside down here, didn't he? His
Yeah.
eureka moment in 1970.
The area theorem. Right after his daughter Lucy was born, he realized the surface area of a black hole's event horizon never decreases.
Which sounded a lot like
Entropy, the measure of disorder in thermodynamics, which always increases according to the second law. This connection was huge.
And Jacob Bokenstein picked up on that, suggesting black holes must have entropy, which means they must have a temperature.
Which seemed impossible for something that supposedly swallows everything. A paradox.
Until Hawking's 1974 bombshell.
Hawking radiation. He brought quantum mechanics into it, these pairs of virtual particles popping up near the horizon.
One falls in, the other escapes.
Exactly. The escaping one carries energy away, making the black holes seem like it's radiating, like it's hot. It means they actually evaporate incredibly slowly.
So they aren't truly black. He even speculated about tiny ones, mini black holes, maybe powering things. Wished he'd get a Nobel for finding them.
He did, though finding one is tricky. But this radiation led to another huge problem.
The information loss paradox.
Right. If the Hawking radiation is totally random, what happens to the information about whatever fell in? Is it just gone?
Which breaks fundamental physics principles, right? Information isn't supposed to be destroyed.
It threatens the core idea of determinism, that the past dictates the future. If information is lost, maybe history books and our memories could just be illusions.
A scary thought. Did he solve it?
Not fully. It's still debated intensely. But later work he did, around 2016, suggested black holes might have subtle hair, these super translations that do carry information out. So maybe it's not lost after all.
Hope remains.
Okay, let's shift gears slightly. Time travel. Everyone loves time travel.
Always a crowd pleaser. We know Einstein showed space and time are linked. Curved space-time.
And special relativity says you need infinite energy to hit light speed, so going faster to go back in time seems impossible that way.
Right. But general relativity, Einstein's other theory, actually opened some weird doors. Kurt Gödel found a solution back in '48 for a rotating universe that could allow time loops.
And things like cosmic strings, theoretical leftovers from the Big Bang.
They could potentially warp space-time enough, too. And then there are wormholes.
The classic sci-fi shortcut. But they do weird stuff, right? Negative mass or energy. They do. Which sounds like fantasy, but quantum mechanics might allow it. The Casimir effect shows that empty space can have negative energy density in tiny regions.
So maybe tiny time warps are possible?
Maybe. But Hawking threw cold water on the idea for macroscopic time travel with his chronology protection conjecture.
Physics itself prevents paradoxes. How?
He argued that trying to create a time machine would cause virtual particles to flood the warp, creating an energy surge that would just destroy it, making the universe safe for historians.
And he actually tried to test it, didn't he? The party.
The famous time traveler party in 2009 sent the invitations after it happened, and he showed up, which, kind of supported his conclusion that practical time travel to the past probably isn't on the cards.
All right, so if we can't easily escape our timeline, what did Hawking think about our future within it, especially here on Earth? He sounded quite concerned.
Deeply concerned. You look at the doomsday clock getting closer to midnight. His own sense of limited time maybe sharpened his focus on humanity's long-term survival.
He basically said Earth is becoming too small for us.
Yeah, pointing to resource strain, climate change getting worse, melting ice, deforestation, population pressure, disease, war, lack of water, species dying off.
He worried about runaway global warming, didn't he? Turning Earth into something like Venus.
A 250-degree Venus with acid rain.
Yeah.
Yeah. And that's just the stuff we're doing to ourselves. There are also external threats. Asteroids.
Like the one that got the dinosaurs. It's not if, but when.
And nuclear war always looming. His prediction was pretty stark.
Almost inevitable that nuclear war or environmental catastrophe cripples Earth within 1,000 years.
That was his assessment. Grim.
So his solution wasn't just fixing things here, was it? It was looking outwards.
Absolutely. Space colonization.
Yeah.
He said staying on Earth forever would be like castaways on a desert island, not trying to escape.
Strong words. He saw it as essential for survival.
Not just survival, but maybe a way to unite humanity. A common goal. Inspire people again, like the moon landings did.
He had a timeline in mind too, right? Moon base, Mars.
Moon in 30 years, Mars in 50, maybe exploring moons of Jupiter and Saturn within 200 years.
Sounds incredibly expensive.
He argued it wasn't, relatively speaking. Maybe 0.25% of world GDP. Tiny compared to other spending. He felt it was affordable.
He even did that zero-gravity flight himself to show it was possible for anyone.
Yeah, in 2007. And looking further out, he was involved in things like Breakthrough Starshot.
Sending tiny probes to other stars.
Tiny nanocraft, pushed by lasers at maybe a fifth the speed of light,
Mm-hmm.
could reach Alpha Centauri in 20 years or so. Take pictures of planets like Proxima b.
That's humanity becoming interstellar, culturally at least.
That's how we saw it, our first steps beyond the solar system.
Okay, one last big topic, artificial intelligence. Another area where Hawking had strong and somewhat cautionary views.
Very much so. He fully believed computers could match and eventually exceed human intelligence, at maybe within 100 years, thanks to Moore's law continuing.
Leading to a potential intelligence explosion, a singularity.
Where AI starts improving itself recursively, rapidly leaving us behind. He called it, potentially, the biggest event in human history.
But also,
The last, unless we learn how to avoid the risks.
what was the main risk, in his view? Malicious AI, like in the movie.
And not necessarily malice, more like competence. An AI pursuing its goals incredibly effectively, even if those goals clash with ours. His analogy was the ant colony versus a hydroelectric dam project.
The ants aren't hated, they're just in the way.
Exactly. And near term, he worried about autonomous weapons. An AI arms race, the Kalashnikovs of tomorrow.
So he wasn't anti-AI, but pro-safety.
Definitely. He signed that open letter with Elon Musk and others in 2015, pushing for safety research, helped set up the Leverhulme Center for the Future of Intelligence. He saw the huge potential benefits too, curing diseases, ending poverty, boosting our own minds.
So it's a race then.
That's exactly how I put it. Our future is a race between the growing power of our technology and the wisdom with which we use it. Let's make sure that wisdom wins.
Wow. We've covered a lot of ground, from the universe just popping into existence to black holes that aren't quite black to, well, our own future among the stars or maybe alongside superintelligent AI.
It's an incredible journey through his mind. And his legacy, I think, isn't just the answers he found, but the questions he asked. Questions that are still driving science forward.
He proved you could travel the entire universe just inside your own mind, even when physically trapped.
And he urged us all, didn't he, to keep questioning, to value science, to work together on these huge challenges.
It matters that you don't just give up. Such simple, powerful words from him.
Absolutely. And he left us with this thought. We are all time travelers journeying together into the future.
So, thinking about everything, Hawking laid out the possibilities, the dangers. Maybe the question for you listening right now is, what kind of future do you want to travel into? And what part will you play in creating it?